February 18, 1944, 11:47 a.m. Somewhere over the snow-covered forests of Bavaria, Germany. Captain James Mitchell grips the controls of his B-17 Flying Fortress as black clouds of flak explode around his aircraft. The entire plane shudders with each near miss. Through the chaos, his bombardier, Lieutenant Robert Chen, lies flat in the nose of the aircraft, his eye pressed against the most secret piece of equipment in the entire American arsenal. His hands move with surgical precision across the Norden bombsight, making infinitesimal adjustments as the aircraft buckets through enemy fire. 22,000 feet below, a critical ball-bearing factory sprawls across the German landscape. If Chen misses, if his bombs fall even 50 feet off target, hundreds of civilians in the surrounding neighborhoods will die. But if he succeeds, if this impossible device actually works as promised, this single factory's destruction could shorten the war by months. Flak rips through the left wing. The No. 3 engine catches fire. Mitchell's co-pilot is screaming to abort, but Chen doesn't move. His world has narrowed to crosshairs, to calculations, to a machine that cost more than the bomber carrying it. Bombs away, Chen's voice crackles through the intercom. This is the story they don't teach in history class. Stay until the end because what happened next shocked everyone, including the enemy who would eventually capture one of these devices and realize they had fundamentally misunderstood American air power. But first, let's go back to where it all began. The year is 1943, and the Allied combined bomber offensive over Nazi Germany is bleeding. Every single day, dozens of American B-17 and B-24 bombers are shot from the sky. Thousands of young men are dying in the frozen stratosphere over Europe. And the terrible truth that keeps generals awake at night is this: most of the bombs are missing their targets. The strategic bombing doctrine seemed perfect on paper. Destroy Germany's industrial capacity, cripple their war machine, force surrender from the air, but reality over the Third Reich is proving far more complicated. Traditional bomb sites require aircraft to fly straight and level for extended periods during the bomb run, making them perfect targets for anti-aircraft fire. Pilots are forced to choose between accuracy and survival. Statistics from early 1943 paint a grim picture. Only about 20% of bombs dropped from high altitude are landing within a quarter mile of their intended targets. A quarter mile. In urban areas, that means bombs intended for factories are instead obliterating neighborhoods, schools, hospitals. The moral weight is crushing. The strategic ineffectiveness is worse. The British have largely given up on precision altogether, switching to nighttime area bombing. They carpet bomb entire city sectors, accepting massive civilian casualties as inevitable. The Americans, committed publicly to precision daylight bombing, face a different kind of pressure. Their doctrine promises surgical strikes. Their reality delivers anything but. German defenses are evolving with terrifying speed. Flak batteries ring every strategic target. Luftwaffe fighters tear into bomber formations with devastating effect. On October 14, 1943, a single raid on Schweinfurt cost the 8th Air Force 60 bombers. 600 men gone in one afternoon. And the ball-bearing factories they targeted. Most survived, production barely interrupted. The situation is desperate. Each bombing raid costs millions of dollars in aircraft and ordnance. More importantly, it costs irreplaceable trained air crews. Young men who survived months of training are dying before completing their 25 mission tours. Some bomber groups are suffering 70% casualties. The mathematics are unsustainable. Behind closed doors, Pentagon planners are running calculations that terrify them. At current accuracy rates, destroying Germany's industrial base will require years and losses that could break American public support for the war. Every day the problem persists, more men die. Every day German factories continue operating. More tanks and aircraft roll off production lines to kill Allied soldiers. Traditional bomb sites use simple mechanical calculators. A bombardier estimates wind speed, altitude, and airspeed, then manually adjusts his sight. Human error compounds at every step. A 5-mile-per-hour miscalculation of wind speed translates to hundreds of feet of missed distance from 4 miles up. Temperature affects air density. Cloud cover obscures targets. Even the Earth's rotation matters at these altitudes. The Army Air Forces desperately need something better, something revolutionary, something that can actually deliver on the promise of precision bombing. Without it, the entire strategic doctrine collapses. Without it, thousands more young Americans will die in flaming aircraft over hostile territory. The stakes could not be higher. The man who would change everything wasn't a general or a scientist. He wasn't even in the military when his invention began taking shape. Carl Norden was a Dutch engineer living in New York, a naturalized American citizen who spoke with a thick accent and preferred the company of machines to people. Born in 1880 in Java to Dutch parents, Norden studied engineering in Switzerland before immigrating to the United States in 1904. While other engineers dreamed of building skyscrapers or automobiles, Norden became obsessed with a peculiar problem: how to drop objects accurately from moving aircraft. His friends thought it was an odd fixation. His family worried about his career prospects. Before World War I, Norden worked for the Sperry Gyroscope Company, developing stabilization systems for ships. He was brilliant but difficult, a perfectionist who would scrap months of work over tiny imperfections no one else could see. His colleagues admired his genius and avoided his temper. When America entered the Great War, Norden contributed to early bombsight designs, but the armistice came before his work saw combat. After the war, while others celebrated peace, Norden couldn't let go of the problem. He opened his own workshop in Lower Manhattan, a cluttered space filled with gyroscopes, gears, and precision instruments. He worked 16-hour days, often sleeping on a cot beside his workbench. His wife barely saw him. His children learned not to disturb father when he was calculating. "It's impossible," other engineers told him. "Too many variables. You can't account for wind at 20,000 feet. You can't stabilize a sight in a vibrating aircraft. Give it up, Carl." But Norden had observed something others missed. He had seen how naval fire control systems used gyroscopes to maintain accuracy on rolling ships. He understood that the same principles could apply to aircraft, but with far more sophisticated implementation. While others saw an impossible puzzle, he saw a solvable engineering problem. It would just require obsessive attention to detail and mechanical precision beyond anything previously attempted. By 1928, Norden had a concept. By 1931, he had a prototype. The Army and Navy were skeptical, but intrigued enough to provide limited funding. His crewmates in the military procurement office thought he was crazy, pouring resources into a device so complex it seemed more like a Swiss watch than battlefield equipment. Officers wondered if this foreign-born engineer truly understood combat conditions, but Norden was determined. Every rejection only strengthened his resolve. Every failed test revealed another variable to account for. He refinanced his house to continue development. He worked through illnesses and family crises, because he knew deep in his engineer's soul that precision bombing was possible. He just had to build the machine that could do it. The idea formation. The breakthrough came during a sleepless night in 1932. Norden sat at his workbench, surrounded by failed prototypes and crumpled calculations. His latest design had performed poorly in tests. The bomb pattern scattered across an entire field rather than the target circle. Most engineers would have seen this as confirmation of impossibility. Norden saw it as data. He began breaking down the problem into its fundamental components. A bombardier needs to know exactly when to release bombs so they fall on target. But the aircraft is moving, and the bombs continue moving horizontally even as they fall, and wind pushes them, and air density affects their speed. The calculations required are beyond human capability in the seconds available during a bomb run. But what if the machine did the calculating? What if, instead of asking a bombardier to estimate variables and make mental adjustments, you created a mechanical computer that continuously solved the bombing equation in real time? The concept was elegantly simple in theory, nightmarishly complex in execution. Norden envisioned a device that would combine gyroscopes for stabilization, an analog computer for calculations, and an automatic pilot connection to actually fly the aircraft during the final bomb run. The bombardier would identify the target, input basic data, and the machine would do everything else. The gyroscopes would create a stable reference platform, immune to the aircraft's movement. A Colsman telescope would provide magnification for target acquisition. The analog computer, using gears and cams, would continuously calculate the correct release point based on altitude, airspeed, wind drift, and ballistic characteristics of specific bomb types. During the final seconds of the bomb run, the sight would literally take control of the aircraft through the automatic pilot, making fine adjustments beyond any human pilot's capability. Norden sketched frantically, his mind racing ahead of his pencil. The device would need to account for trail, the angle behind the target where bombs must be released. It would need to compensate for drift, wind pushing bombs sideways. It would need to calculate for different bomb weights and shapes. Every variable required mechanical computation built into the device itself. But how do you actually make this work? How do you build an analog computer accurate enough for these calculations? How do you create gyroscopes stable enough to maintain reference in a vibrating, maneuvering bomber? How do you make it robust enough for combat conditions yet precise enough for surgical accuracy? Norden realized he needed unprecedented manufacturing precision. Gears would need to be machined to tolerances of 10,000ths of an inch. Gyroscopes would need near-perfect balance. Every component would need to be hand-assembled by master craftsmen. The device would be as much art as engineering. He also understood the human factor. The sight couldn't be too complex to operate under combat stress. It needed to be intuitive enough that a 22-year-old bombardier, scared and cold in a battle-damaged aircraft, could still use it effectively. The interface between man and machine required as much thought as the machine itself. Over the following months, Norden refined his concept. He consulted with pilots and bombardiers, learning what they actually needed versus what engineers thought they needed. He studied ballistics tables and atmospheric science. He visited factories to understand what could be manufactured reliably. The device taking shape in his mind represented the absolute cutting edge of mechanical engineering. His colleagues remained skeptical. "Carl, you're describing a machine that would cost more than the aircraft carrying it. You're talking about manufacturing precision that barely exists in the watch industry, and you expect this to work while being shot at?" Norden's response was simple. "Then we make it work. Because the alternative is unacceptable." The construction of the first true Norden bombsight consumed 3 years and pushed mechanical engineering to its absolute limits. Norden's workshop in Manhattan became a laboratory of precision, unlike anything outside the finest Swiss watch manufacturers. Finding craftsmen capable of the required work proved nearly impossible. Norden interviewed dozens of machinists before finding a handful with steady enough hands and patient enough temperament. These men would spend entire days machining single gears, checking dimensions with micrometers, rejecting pieces that were off by microscopic amounts. One gear train assembly required 43 separate parts, each machined to tolerances that made conventional manufacturing seem crude by comparison. The gyroscopes presented particular challenges. These spinning devices needed to maintain perfect orientation regardless of the aircraft's movement. Norden designed them with precision bearings that cost more than a car. The gyroscope housings were machined from solid brass, then hand-polished to mirror finishes. Each gyroscope was balanced and rebalanced until it could spin for hours without deviation. The analog computer, called the baseball by operators due to its spherical stabilization platform, required mechanical genius. Norden designed a system of gears, cams, and differentials that performed continuous trigonometric calculations. As inputs changed, altitude, airspeed, wind, the gears rotated, automatically updating the solution to the bombing equation. It was mechanical calculus, bronze and steel solving problems that would later require digital computers. Money became a constant crisis. The Navy provided some funding, but not enough for Norden's perfectionism. He sold his personal belongings, borrowed from anyone who would lend, and begged components from manufacturers. His wife Sarah took a job to support the family. His children wore hand-me-down clothes. Everything went into the bomb sight. Working through the night became routine. Norden's workshop glowed with lamplight until dawn, neighbors complaining about the constant machine noise. His assistant, Theodore Barth, a Swiss craftsman with 30 years of watchmaking experience, often slept on the floor rather than leave complex assemblies mid-construction. They spoke in languages of precision, tenths, hundredths, thousandths of an inch, that would have been meaningless to outsiders. Technical challenges emerged constantly. The first gyroscopes drifted after 30 minutes, useless for long bomb runs. Norden redesigned the bearing system 3 times before achieving the necessary stability. The gear trains in the computer kept binding under temperature changes. He switched to exotic alloys that maintained dimensional stability across wide temperature ranges. Materials so expensive they required special authorization to obtain. The automatic pilot interface nearly broke him. Making the bombsights calculations control the aircraft demanded precise electrical signals and mechanical servos that didn't exist in reliable form. Norden ended up designing those too, creating servo motors and control amplifiers as side projects to his main work. The scope kept expanding, the complexity growing exponentially. By 1935, a functional prototype existed. It weighed 50 pounds, contained more than 2,000 moving parts, and looked like something between a telescope and a mechanical brain. Norden handled it like a newborn, his hands trembling slightly as he made final adjustments. Barth stood beside him, wiping machine oil from components with white cloth, checking and rechecking every connection. 5 years, Barth said quietly. 5 years to build one site. Then we build it right, Norden replied. Because men will trust their lives to this. We owe them perfection. The cost had been staggering. The prototype alone consumed $50,000, more than a Flying Fortress bomber would cost a decade later. Military accountants were horrified, but the device worked on the test bench, its calculations matching theoretical predictions within margins so narrow they seemed impossible. The question now was whether it would work in an actual aircraft, under actual bombing conditions. Theory was about to meet reality at 20,000 feet over the Chesapeake Bay. If it failed, 5 years of work would be wasted. If it succeeded, it would revolutionize warfare. August 7, 1935. Aberdeen Proving Ground, Maryland. A Martin B-10 bomber circles over the Chesapeake Bay at 10,000 feet, carrying the most expensive piece of equipment most of the observers below have ever seen. On the ground, Army and Navy brass gather around a target circle painted on a sand spit, jutting into the bay. The circle measures 100 feet across. Conventional bomb sights of the era could maybe hit within a quarter mile from this altitude. Norden has promised accuracy measured in feet. The officers are polite, but their skepticism is palpable. They've seen too many miracle weapons fail. Inside the bomber, Lieutenant Commander Frederick Entwistle, a Navy bombardier selected for his steady nerves and skeptical nature, lies prone behind Norden's bomb sight. Beside him, Norden himself makes last-minute adjustments, his hands shaking slightly. This isn't nerves, it's the tremor he's developed from years of precision work. He trusts his machine more than he trusts human operators, even trained ones. Altitude? Norden asks. 10,200 feet, the pilot calls back. Airspeed? 160 knots, steady. Norden makes minute adjustments to the site's altitude and airspeed inputs, his movements precise despite the tremor. The gyroscopes inside the device are already spinning, creating their stable platform. He steps back, giving Entwistle control. Through the Colesman telescope, Entwistle finds the target circle. It looks impossibly small from 2 miles up, a white dot on brown sand. He adjusts the site's crosshairs, centering them on the target. The site's computer begins processing, gears turning inside the baseball-shaped platform. Beginning run, Entwistle announces. The site takes control of the aircraft through the automatic pilot. The pilot's hands remain on the controls, but he can feel the aircraft making corrections beyond his input. Tiny adjustments smaller than any human could make, keeping the site's crosshairs perfectly aligned. On the ground, observers watch through binoculars. Some check stopwatches. Others make notes. Most simply wait, having seen countless tests over the years, almost all disappointing. Inside the bomber, Entwistle watches the site do things he's never seen before. The crosshairs remain locked on target despite wind gusts and minor turbulence. The device is computing continuously, adjusting for every variable. He's along for the ride, no longer bombing but witnessing the machine bomb. A series of lights on the site illuminate in sequence. The computer has solved the bombing equation. Release is imminent. Entwistle's finger hovers near the manual override just in case. Then, automatically, the bomb bay doors open. The site waits 3 more seconds, compensating for the door's drag effect on airspeed, then releases. A single 100-pound practice bomb falls away, tumbling briefly before stabilizing into its ballistic trajectory. From 10,000 feet, it takes nearly 30 seconds to reach the ground. 30 seconds of silence in the bomber. 30 seconds where Norden closes his eyes, lips moving in silent calculation, checking his machine's math in his head. The bomb strikes 15 feet from the center of the target circle. The silence on the ground lasts perhaps 2 seconds. Then chaos. Officers are running toward the impact point, measuring, checking, rechecking. 15 feet. From 2 miles straight up, some are laughing in disbelief. Others are already calculating strategic implications. In the bomber, Entwistle turns to Norden, his face pale. "Sir, I barely..."